Welcome! Today we talk about the classification of matter. The objective for today's lesson is that by the end of this, hopefully, you can distinguish between pure substances, mixtures, and solutions using common examples. And we're actually going to go into a fair amount of depth here, really getting into how the classification of matter works. So what is a classification of matter? First of all matter, doesn't matter what it is. If we have a sample of matter, we can classify it or assign it into one of the following categories or groups. So if I take a look at the diagram, I can take matter, any sample of matter, and I can say whether it is a pure substance or a mixture. If it's a pure substance, I can further classify it as either an element or a compound. Or if it's a mixture, I can then take a look at it and say whether it's a homogeneous or homogeneous mixture, or if it's a heterogeneous mixture. Now, why does this matter? Why do we care about classifying or assigning a sample of matter to one of these categories? It's because the terminology is important. When I say compound in chemistry, it means something. And when I say element, it means something. And when I say solution, it means something. So these words you've probably heard before when talking about chemicals actually have a proper use, and it's saying something specific about the chemical, about the matter that we're looking at. So we need to learn more about it so we know what the correct terminology is. And when I say element, you know what that means in terms of what the particles are doing and how the particles are. All right, so we can tell which group a sample of matter fits into by considering the particles, its physical properties, and its chemical properties. So these are the things that we're going to consider when we take a look at these different things. In a pure substance, all particles are the same. So going back here, when I take a look at my first category to the left, right, matter can be classified into a pure substance or a mixture. In a pure substance, every particle is the exact same. This means a pure substance cannot be separated into different substances by a physical process. We're going to talk about physical processes later on, okay? But by physical process, I mean things like distillation, filtration, crystallization. So I'll give you an example. If I had salt water, right, I could actually separate the salt from the water by letting the water evaporate out, and I'd be left with the salt crystals. Okay, so that would be a mixture because I have more than one thing. That could be separated by a physical process. Pure substances cannot because I have only one type of particle there. So here I have some pictures. These are elements, and this over here is a compound. So in elements, every single atom is the same. So in this element, I have just the red atoms, or it's being shown as red. And then here I have the purple atoms that are together, right? Two atoms together, bonded together, but every particle is still the same, made up of the two purple spheres, right? Two atoms that are the same. If I take a look at a compound, every particle of this compound is the same as well. In fact, this would be a representation of water, H2O. I have two hydrogen atoms and one oxygen atom, but every particle is the exact same particle, which is what I have in a pure substance. Every particle is the same. So, and I wish I would have erased this before I started, but it is what it is. If I take a look at this diagram here and I try to figure out which one of these are pure substances based on the pictures of the particles. A, for example, would be a pure substance, and it's a pure substance because every particle is the same. It has two smaller atoms and one large atom. We're not saying what element those atoms are, but you can see that every particle, every unit of this is the same. If I take a look at this, yeah, this is also a pure substance because I have the same particle. Sure, it's rotated, right? But it's one black and one white sphere, one black and one white atom. Is C a pure substance? Well, no. I have two different types of particles going on here, right? I've got this and I have this. D, no, that's not a pure substance either. Now let's go one step further. I want to ask you here, between E, F, G, and H, which one of these is not a pure substance? And the answer is G. I have more than one type of particle here, right? I've got this particle, which is the same as this one, and then I have this particle as well. So because I have more than one type of particle, okay, this is not a pure substance for G. So in an element, So we're getting more specific here. Under pure substance, we have elements, and in an element, every atom is the exact same. You can tell something is an element because it is on the periodic table of elements. So on the periodic table of elements, we have all of the different elements that make up matter, right? It's the building blocks of everything in terms of substances is made up of elements. So if it's on the periodic table of elements, we know that it's an element, and within a sample that is an element, every single atom, which we saw as like balls in that last diagram, every single atom is going to be the same. Elements cannot be broken down chemically. They are as small of a unit as you can get by chemical reaction. So once I have an element, I can't chemically decompose it any further. That again is like the building blocks. It's like if you're taking apart Lego, once you get to a single Lego block, that's like your element. You can't break that apart any further. Okay, they're the basic building blocks of matter. So what I have circled here is magnesium, for example. So if I have a piece of magnesium, right, that would be an element. If I had, let's say, a chunk of aluminum, like the cans are made of, okay, that would be an element. And within that chunk of aluminum, every single atom is the same. It's an aluminum atom. So if I were to take a look at this diagram here and try to figure out for this which ones are elements, okay, so the question here is, of all of these samples, in which one are all the atoms the same? And so, for example, in E, every single one of these is the exact same. The same thing with F. Every single one of these atoms is the same. So this would be an element. H would also be an element. Okay, so if you take a look at the last row, which two of these would be samples that are elements? And the answer is J and K. These are both elements, right? Because they all have just one type of atom going on. So some examples of elements: gold, silver, oxygen, helium, copper, aluminum, graphite, which is actually carbon. These are all things that are found on the periodic table of elements. And within samples of this, every single atom would be the exact same. So if you're writing with a pencil right now, you're actually smearing carbon on the piece of paper, because the lead within a pencil, it's not actually lead, it's graphite, which is just carbon. Interesting enough, diamonds are also carbon. So some elements can actually have more than one possible form. We call these allotropes, but that's a different lesson entirely. But like oxygen that you're breathing in right now, that's an element, right? The air isn't, but the oxygen within the air is. If you had an oxygen tank, right, like for medical purposes, for example, well, then that is almost entirely pure oxygen. That's elemental oxygen. If you have helium, like in a helium balloon, then again, you have a pure substance. Copper, like the copper pipe is made out of, right? That is an element. So within a sample of copper pipe, every single atom is the same if you have pure copper. Okay, moving forward. A compound, unlike an element, is made up of two or more elements, and they are chemically bonded together. So the atoms of those two or more elements are chemically bonded together to make particles that are all the same. Compounds can be chemically separated into elements by a chemical reaction. So here are a few examples of common compounds. So water being like the most famous compound, right? And probably one of the most important compounds to our lives is two hydrogens and an oxygen, H2O. Now I can actually chemically separate water into hydrogen and oxygen. I can do that through a process called electrolysis, where I put some current through water and it actually will separate into hydrogen and oxygen. And we use something called a Hoffman apparatus for this. Maybe take a look at this video here. Okay, carbon dioxide that's being breathed out of your mouth is also a compound, and it's made out of carbon atoms and two oxygen atoms, but those atoms are bonded together to make molecules, to make that compound. So in a sample of pure carbon dioxide, every single particle, every single molecule is the same. That's going to be one carbon and two O's chemically bonded together. Hydrogen peroxide is another one, H2O2. Now, hydrogen peroxide, we can break that down into hydrogen and oxygen. In fact, something that you can do at home that's really neat is you can break down hydrogen peroxide into oxygen gas and water. And if you have 3% hydrogen peroxide, normal hydrogen peroxide you use on cuts and stuff, you put a little bit of yeast in there, it will start bubbling. And the bubbles that are forming from that are actually oxygen gas that is being released as it makes water and O2. So I can go through this chemical process in order to actually make an element product, to make smaller pieces. I can break it down chemically, which is true for a compound. So going forward, here's my pure substances, and we've talked about elements where every single atom is the same, and then compounds, which is made out of more than one element chemically bonded together, but again, every particle is the same. So if I take a look at this diagram here, let's talk about which ones are compounds. So for example, if I look at A, I have more than one type of atom, right? I've got the small ones and the larger ones, but they're chemically bonded together to make every particle the same. So A would be a compound. B would also be a compound because again, I have more than one type of element, more than one type of atom, but every particle is the same. So that is a compound. C is not a compound. D is not a compound. I have both a compound and an element mixed together in D. All right, let's take a look at this row right here. You tell me from this row, E, F, G, or H, which one, well, none of them are. Joking. Okay, let's look at the last row. Between I, J, K, and L, which one of these is a compound? And the answer is L is the only one that is a compound. This is an element, this is an element. I almost looks like it is, but you'll actually notice that I have some different particles here. I have particles that are 2 atoms and particles that are 3 atoms. This would be kind of like a mixture almost of carbon monoxide and carbon dioxide or something like that. Okay, so you've got more than one thing mixed together. So what are some examples of compounds? Well, water is a classic example. We know that water is H2O. Table salts is an example of a compound. It's sodium and chlorine chemically bonded together to make something called sodium chloride. So table salt is the common name for sodium chloride. Sucrose is another compound that's made out of carbon, hydrogen, and oxygen. So this is kind of a crazy molecule, but if you have 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms all bonded together, okay, and they're actually bonded together in a specific way, then you've got sucrose. But within sucrose, every single particle, every single molecule of sucrose is the same. Baking soda is a compound. That's sodium hydrogen carbonate. So that's 4 different elements bonded together to make that compound. Carbon dioxide that you're breathing out of your mouth is CO2. And then acetone, for example, is C3H6O. So these are all examples of compounds where more than one element is bonded together to make particles that are all the same. Now, I wrote those formulas out. You don't even understand how formulas work at this point. That's okay. I just want you to realize that I have more than one element bonded together to make all the particles the same. Okay, now let's talk about mixtures. In mixtures, we have 2 or more pure substances that are mixed together. Not every particle is the same. And we can actually separate mixtures by using a physical process. So we can actually take mixtures and then separate them into their pieces through processes like, for example, distillation. In a mixture, each pure substance still has its own unique chemical and physical properties. So unlike in a compound, where you don't actually have the elements showing their unique properties, it's now the compound's properties. In a mixture, you see the properties of the different things. So for example, if you have some Coca-Cola, right? You can actually tell that there's different stuff in there that has its own unique properties. So for example, there's sugar in the Coke that makes it sweet. If it's fizzy, that's carbon dioxide that's making it fizzy. It's wet because of water in there. So you have all these different pure substances that are in there mixed together, and each one of those pure substances is showing its properties. Okay, it still has its properties. which is completely different than a compound. And I'm going to back up for a second here to talk about compounds. Let's consider table salt as an example. It's a good classic example. These are bonded together. The sodium and the chlorine are now together in one unit, chemically bonded. That's very different than if I had sodium and chlorine as two separate elements. Sodium is this incredibly reactive element that if it even touches water, it can burst into flames. Okay, it reacts very, very quickly with water. And then chlorine is actually poisonous. It's a poisonous gas. So you can imagine like sodium, which kind of can light on fire when it touches water and it's very reactive, and chlorine that's also very reactive and can kill you. It's poisonous, right? That's really weird that together, when it's chemically bonded, this makes salt that we eat and it's delicious and good on fries. But it's different. When it's chemically bonded together, it now has different properties. It's no longer reactive with water. It's no longer poisonous in small quantities, right? It's not the same as chlorine gas. It now has new properties. So in a compound, you don't have the elements properties anymore. You have the compound's properties. But in a mixture, you still see all of the properties of the pure substances that are mixed together inside of the mixture. So let's take a look at this, and again, considering the particles, talk about which ones are mixtures. So in other words, which one of these has more than one type of particle present? So if I take a look at the first row, this is not a mixture, this is not, this is a mixture because I have more than one type of particle present. And this is also a mixture because I have more than one type of particle present. All right, in the second row, which one of these is a mixture? And the answer is G. For G, I have two different types of particles going on, right? I've got this type of particle and this type of particle. So this is a mixture of a compound, right? Compound and an element going on there. Mixtures can be classified into two different groups. We either have homogeneous or homogeneous, depending on how you want to say it, or heterogeneous mixtures. Now, another word for homogeneous mixtures, especially when they're a liquid, is that it's a solution. And then a heterogeneous mixture is sometimes called a mechanical mixture. Let's talk really briefly about this prefix of homo. Homo means same, hetero means different. So when I say homogeneous mixture, I'm saying it all looks the same. Well, if I'm saying heterogeneous mixture, that means you can see different parts. There's different parts that look different. So in a homogeneous mixture, you can see divisions between substances. Sorry, you cannot. Oh, yeah, definitely cannot see divisions between substances. It all looks the same or uniform, so you can't tell the different parts. The particles are so evenly distributed, okay, they're all kind of like spread out and mixed together so well that it all looks the same. But in a heterogeneous mixture, that's not the case. You have groups of particles of one pure substance that's together, and then groups of particles of the other pure substance that's together. And so as a result, you can see these distinct boundaries, these different parts to it. So some examples of homogeneous mixtures. Air is a great one. The air around you is a homogeneous mixture, right? It's made of nitrogen and oxygen and carbon dioxide and methane. You've got like water, right? You've got all these different things in the air around you, but all you see is just like transparent nothingness. And that's because it's all mixed together very, very well. And also, obviously it's transparent. So air is an example of a homogeneous mixture. Steel is iron and carbon mixed together, but it all just looks uniform. You can't see the carbon and the iron atoms being separated in any way. It just looks like one thing. Okay, wine is a good example. Rain, when it's like rainwater, collected rainwater, okay, that would be a homogeneous mixture because there's other stuff in the water as well, like minerals and acid, possibly. Like rainwater is slightly acidic and pH of like 5.6 normally or something around there. So essentially, all those things are homogeneous mixtures. When I look at heterogeneous mixtures, you can see the different parts. You can see different bits to it. So for ice water, you can see the part that's actually ice cubes, and then you can see the water, and it's separated. That's a heterogeneous mixture, okay? You can actually see different parts. Cereal and milk, that's heterogeneous. Soil, oil and vinegar. Now, I do want to talk about the ice water briefly because I know that you guys might think, well, isn't it all water? We're going to assume also that in that, maybe we have some impurities and stuff as well. But in any case, it is heterogeneous that we can see the different parts. Here's another kind of diagram to show you this. In heterogeneous, well, this is actually kind of a lot more of the same, but cereal and milk, ice and soda, soil, blood, again, we can see the different parts to this. You can see different things. Well, in homogeneous, vodka, right, which is like clear alcohol, where we have 40% ethanol, which is alcohol, and then water and some other stuff too, but it all just looks clear and together. Air, again, rainwater, these are all examples of homogeneous things. Some mechanical mixtures have a uniform-ish appearance unless you look very closely, but if given time, the particles will separate or settle. So within mechanical mixtures, we actually have these kind of like sub kind of categories that we can go into that we talk about in everyday life a little bit. So one thing, if we have the particles will settle over time, we call this a suspension. You might actually see this with medication. So for example, children's Tylenol is a suspension. It actually says on there, acetaminophen suspension. So what that means is that the acetaminophen is actually like suspended in particles throughout that solution. And that's why it's really important that you shake it before you actually end up using it. A lot of medications are like this. Same thing with like the antibiotics, you know, the wonderful penicillin that tastes like banana, that really, I kind of like it. Synthetic banana flavoring, that is a suspension. So you add water to it, you shake it, right, for that kind of stuff. And then from there, you've got your suspension. But over time, if you leave it, you don't shake it, it will settle down to the bottom. This is a type of heterogeneous mixture. Muddy water would be the same. Fog, mustard. You guys ever try mustard when you haven't shaken it and it just comes out, you know, like the liquid first, you don't get any of the mustard in there? That's because mustard is essentially a suspension. Well, if you have a colloid, colloids are a bit different than suspensions, that the particles will not settle or separate very much over time. So typically this has to do with the particles being much, much tinier, but they won't actually separate, or maybe there's something called an emulsifying agent in there that keeps it all mixed together. So examples of this are mayonnaise, milk, or lotion. You guys should look really closely at milk. It's interesting because if you look really closely at milk, you can actually see the little like fat globules in there, right? So yeah, it's actually a heterogeneous mixture. Even though you might think it's homogeneous, it's heterogeneous because you actually can see some separate particles or parts. So under heterogeneous mixture, just kind of going back to this diagram, under heterogeneous mixture, we also have these little subcategories of suspension, which means that it kind of looks somewhat uniform-ish unless you get really close. But as time goes on, it separates. You'll have some on the bottom of that mixture and other stuff on the top. And then colloids, where still you can see little bits if you look close, little divisions, but it stays together unlike a suspension. Okay, so how can you tell the difference between a solution, a suspension, or a colloid? Well, here's kind of the ways that you can distinguish between these three things using observations or empirical evidence. If you try to shine a flashlight or a beam of light through a solution, the light will travel through without being like scattered or bounced around. It won't dim very much through a solution. So you can normally like see through liquid solutions quite well, or gaseous solutions. It will travel through, unlike for a solution, suspension, sorry, is what this should say. Just going to cross that out and put suspension. Unlike for a suspension or a colloid, where it will scatter the light. So when you have light going through a suspension or a colloid, it's going to get very, very dim. Okay, and you might not even be able to see the light coming through because the light is getting scattered by the particles that are quite large compared to in a solution for the suspension or a colloid. A solution will separate in time, a colloid will not. So if you have a solution, this again actually should say suspension, I'm sorry. A suspension, if you take a suspension and leave it for a certain amount of time, it's going to separate into layers. A colloid will stay somewhat mixed together. So between solution, suspension, and colloid, that's how you can tell them apart. Okay, a solution, light will travel through, no problem. Suspension, colloid, it won't. If you leave something and it settles into two different parts, well, then it's a suspension. Okay, if it doesn't settle into two different parts, but it does scatter light, light can't travel through, well, then it's a colloid. All right, last kind of diagram here is a little bit of a summary of all of this. So first of all, we have any matter can be categorized as either a mixture or a pure substance. So if it can be physically separated by something like distillation or crystallization, then yes, it's a mixture. If it can't, then no, it's a pure substance. If it's a pure substance, the next question is, can it be chemically decomposed or separated into smaller parts? If the answer is no, well then you've got an element. It's one of the periodic table of elements. If it can be decomposed into smaller parts, then it's a compound. Okay, if you have a mixture, is the composition uniform? Does it have one appearance? If the answer is yes, it's homogeneous. If the answer is no, well then it's heterogeneous or a mechanical mixture. For heterogeneous, we also have sub kind of groups of that, of suspensions, where over time we'll have particles separating, okay? And then colloids, where it scatters light, light can't travel through, but it does not separate over time. All right, that's it for this lesson. Have a good rest of your day.